Look at your breath on a winter morning. That pale cloud hanging in the air at -10 degrees is, to the universe, almost indistinguishable from boiling. The average temperature of everything, every galaxy, every void, every cubic meter between the stars, is 2.7 degrees above absolute zero. Somewhere out there, it is colder still. There are 7 layers of cold between your body and the floor of the universe, and each one is stranger than the last. Dim the lights. Let your hands rest. Breathe in slowly, and let the room around you soften into quiet. Tonight, you are going to travel outward through every layer of cold in the universe, from your own skin to the shadow of the Earth to a nebula colder than space itself, and understand why warmth is the anomaly, not cold. Before we dive in, if you love exploring the quiet extremes of the cosmos as much as we do, take a second to like the video or subscribe and tell me where you're listening from and what time it is. I read every comment. Now let's begin. To understand what cold actually is, we have to start by unlearning almost everything your body has taught you about it. Your body knows cold as an experience, a draft under the door, the shock of stepping onto a tile floor in bare feet, the bite of winter air on your cheeks that makes your eyes water. For your body, cold is a sensation, a messenger, a warning. Your nerve endings are built to notice temperature differences relative to your own skin, which lives at about 37 degrees Celsius. Anything significantly below that feels cold. Anything significantly above feels hot. And that is the entire range your species has ever needed to understand. But that is not what cold is. Not really. Cold, in the language of physics, is not a substance. It is not something that flows into your house through a cracked window. It is not something that exists on its own, the way water exists or stone exists. Cold is the absence of something. It is the absence of motion. It is the absence of the trembling, shivering, jittering dance that atoms and molecules perform when they are alive with energy. Heat is the dance. Cold is the stillness when the dance slows down. And the deeper the cold, the more profound the stillness becomes. That word, stillness, is worth sitting with for a moment. Because when you imagine the air in the room around you, you probably picture it as something calm, something at rest, a still room, a quiet night. But the air molecules in front of your face right now are moving, on average, at about 500 meters per second. That's faster than the muzzle velocity of most pistol bullets. And the molecules are colliding with each other billions of times per second. They are bouncing off your skin, your eyelashes, the walls of your lungs in a relentless, invisible hailstorm. What you perceive as stillness is, at the molecular level, one of the most violent environments you could possibly be inside of. Now take that image and begin to turn down the volume. Slow the molecules. Let them move less. Let them collide less often. Let them drift more gently past one another. As they slow, the air cools. You feel this sometimes on a frigid morning. That sensation of the air feeling thinner, somehow less alive, as though the world has been dialed down a notch. And that is exactly what is happening. The molecules are moving less. Their average kinetic energy has dropped. Your skin registers the difference as a sensation. Cold. Keep turning the dial. Keep slowing the molecules. Remove more energy from them. Force them to dance less and less. Eventually, you reach a theoretical limit, a point below which nothing can go, a point where the molecules are not just moving slowly, but are as motionless as the laws of physics will allow. That limit is called absolute zero. and it sits at minus 273.15 degrees Celsius, minus 459.67 degrees Fahrenheit, 0 on the Kelvin scale, named for the 19th century Scottish physicist William Thomson, who became Lord Kelvin in 1892 after a career spent mapping the thermodynamics of the universe. Absolute zero is not arbitrary. It is not just the coldest temperature humans have happened to encounter. It is a wall built into the architecture of reality. You cannot pass it. You cannot reach it. You can approach it. Modern laboratories have come within a billionth of a degree of it. But you cannot actually touch it, because to drain the last flicker of motion from an atom requires an infinite amount of effort. The universe has a flaw, and every temperature you have ever experienced, every fire you have ever sat near, every ice cube you have ever held is a number measured up from that flaw. When you hear the weather report say it is minus 10 degrees Celsius outside, that sounds cold. Your body agrees. But measured from the true bottom, from absolute zero, minus 10 degrees, Celsius is 263 Kelvin, 263 degrees above the floor. In the cosmic scheme of things, that is not cold at all. That is warmth. That is a livable, almost tropical number compared to what waits beyond Earth's atmosphere. Your winter morning, with your visible breath and your gloved hands and your chattering teeth, is, from the universe's perspective, a warm afternoon. This is the first fact we have to reckon with before we can go any further. Earth is warm. Not just comfortably warm, extravagantly warm, bizarrely, almost suspiciously warm. Your planet is a small blue furnace floating in an ocean of cold, and everything about your experience of temperature has been shaped by the fact that you live on top of a fire. Let's make that concrete. The average surface temperature of Earth is around 15 degrees Celsius, or about 288 Kelvin. The average temperature of the universe, every cubic meter of space, averaged together, is 2.7 Kelvin. That means Earth is more than 100 times warmer than the average temperature of the cosmos. You are not living at the universe's baseline. You are living at a hundredfold anomaly. And what keeps you there? What keeps your planet from falling into the cold that surrounds it on every side? 3 things mostly. The first is the sun, 93 million miles away, pumping out roughly 3.8 times 10 to the 26th watts of energy every second. A tiny fraction of that energy reaches Earth, about 1 part in 2 billion. But that tiny fraction is enough to keep your oceans liquid and your lungs functioning. The second is Earth's atmosphere, a thin shell of gas that traps some of that solar energy long enough for it to circulate, warm the land, warm the seas, warm you. The third is the molten interior of the planet itself, a core of iron and nickel at about 5,000 degrees Celsius, radiating heat outward through the mantle and crust for 4.5 billion years and counting. Strip any one of these away, and things begin to change quickly. Strip away all 3, and your planet becomes indistinguishable from the cold that surrounds it. The blue marble you see in photographs would become, within a few 100,000 years, a frozen stone drifting at a few degrees above absolute zero. Earth is not naturally warm. Earth is actively heated. And the machinery of that heating has been running, without interruption, for longer than there have been continents. Now, here is where your intuitions begin to fail you. You have probably seen photographs of astronauts in space. They are wearing suits, yes, and those suits look thick and protective, but the overall impression is of humans floating serenely in a bright, empty expanse. When the sun is visible, space looks almost luminous. The astronauts are bathed in light. They seem comfortable. You have also probably seen somewhere the often cited statistic that space is cold. Minus 270 degrees Celsius, perhaps. Sometimes the number is given as minus 255, sometimes as minus 454 Fahrenheit. You have probably nodded along and thought, yes, space is cold, obviously, and then moved on. But here is what almost nobody tells you. Space, as a temperature, is not really a meaningful concept the way you think it is. The cold of space is not like the cold of a winter morning. It is not air that would rush into your lungs and freeze them. It is not a substance at all. Space is almost entirely empty. Space is, for all practical purposes, nothing. And nothing does not have a temperature in the ordinary sense. In the average cubic meter of interstellar space, there are only about 1 million atoms, which sounds like a lot, until you realize that in the same cubic meter of the air around you, there are roughly 25 trillion atoms. That's a ratio of about 10 to the 19, a million billion times denser than space. So when we say space is 2.7 Kelvin, what do we actually mean? We mean something subtle and something strange, and something that took humanity most of a century to understand. We mean that if you place an object in deep space, far from any star, far from any planet, and you wait long enough for it to reach equilibrium with its surroundings, it will settle at a temperature of about 2.7 Kelvin. Not because something cold is cooling it down, but because the only radiation reaching it from every direction is the faint, uniform glow left over from the birth of the universe. A glow that is itself at 2.7 Kelvin, and that, by absorbing and re-emitting, sets the thermal floor of everything it touches. That glow has a name. It is called the cosmic microwave background, and it was discovered almost by accident in 1964 by two radio astronomers in New Jersey named Arno Penzias and Robert Wilson. They were trying to calibrate a large horn antenna at Bell Labs in Holmdel, and they kept picking up a persistent hiss of microwave noise they could not get rid of. They checked everything. They cleaned pigeon droppings out of the antenna. They rewired the equipment. The hiss remained. Eventually, after a chance conversation with physicists at Princeton, they realized what they were hearing. They were hearing the echo of the Big Bang, the last whisper of the fireball that had filled the universe 13.8 billion years ago. That whisper had been stretching and cooling ever since, until by the time it reached their antenna, it had cooled all the way down to 2.7 Kelvin. Penzias and Wilson won the Nobel Prize in 1978 for that discovery. And what they had found, without quite realizing it at first, was the temperature of the universe itself. The temperature of the empty places between the stars. The temperature that every object will eventually drift toward, unless something else is actively heating it. 2.7 Kelvin, 2.7 degrees above absolute zero, 270.45 degrees Celsius below the temperature of your skin. That is the baseline of reality. That is the floor. That is what the universe is, once you strip away the stars and the planets and the furnaces and the living bodies. That is the dark you were born inside of. And it is this number, this seemingly small number, that we are going to spend the next several hours understanding. Because 2.7 Kelvin is not simply cold. It is cold in a way that defies every instinct you have about what cold can do. It is cold in a way that human biology was never built to survive, was never built to imagine, was never even built to fear. Your body has a vocabulary for winter. It does not have a vocabulary for this. Before we go any further, there is one more foundational idea we need to plant, because it will reappear in every layer we visit from now on. In the cold of space, The usual rules of how you lose heat do not apply. On Earth, when you step outside in winter, you lose heat in three main ways. You lose it through conduction, direct contact with cold surfaces, like a metal railing that stings your bare hand. You lose it through convection, cold air flowing past your skin, carrying warmth away, which is why a windy day feels colder than a still one. And you lose it through radiation, invisible infrared light streaming off your body in every direction, the way a hot stove radiates warmth, even without touching you. In space, the first two of these vanish. There is no air to conduct heat away, or almost none. There is no wind. There are no cold surfaces to touch. An object in the vacuum of space loses heat only by radiation, only by emitting infrared light into the surrounding void. And radiation is, compared to conduction and convection, extraordinarily slow. This is why astronauts on a spacewalk do not instantly freeze solid. This is why the International Space Station, in the shadow of Earth, does not plunge to 2.7 Kelvin within seconds. Heat leaks out of objects in space at a leisurely pace, while warmth from the sun pours in at full force. The vacuum is, in some strange way, an insulator. It is both the coldest environment imaginable and, paradoxically, one of the hardest environments to actually cool down in, because you cannot touch anything to bleed the heat away. This is going to become important, because as we descend through the layers of cold, as we move outward from Earth into the shadow, and then beyond the shadow into deep space, and then beyond deep space into the deepest cold in the universe, we are going to encounter situations where the absence of matter does not protect you from the cold. It delivers you to it, slowly, inevitably, by a process so patient it feels almost deliberate. The vacuum does not hate you. The vacuum simply does not notice you. It will take the heat out of your body eventually, in the same way water will eventually smooth a stone. You do not need to fight the vacuum. The vacuum will win by waiting. And that is the first thing the cosmos knows that your body does not. That cold in its deepest and truest form is not an event. It is a condition. It is the condition the universe defaults to when nothing is being actively burned, nothing is being actively fused, nothing is being actively alive. The stars are temporary. The warmth of your planet is temporary. You are temporary. The cold is what was here first, and the cold is what will still be here when everything else has gone dark. Hold that in mind as we begin our descent. We are going to move outward through 7 layers, starting at your own skin and ending at a place so cold that it violates even the expectation of what the universe itself should be. At each layer, we will linger. We will examine what it feels like, what it does to matter, what it does to a human body if one were unlucky enough to be placed there. We will meet the scientists who first measured each layer, and we will hear what they found. We will ask, at every step, the same question. What does cold actually do when there is enough of it? Before we step off Earth, we need to finish mapping the ground beneath our feet. Because the story of cold does not begin in space. It begins here, on the surface of your planet, in the small laboratory experiments and the freezing expeditions, and the careful thermometers that taught humanity what cold even means. And without that foundation, the numbers that follow will slide off you like water. You will hear minus 270 degrees and nod, and it will mean nothing, because you will have no frame of reference. So let us build that frame carefully. Start with the coldest temperature ever recorded on Earth by a weather station. The place is Vostok Station, a remote Soviet, now Russian, research outpost on the East Antarctic plateau, sitting at an elevation of more than 3,400 meters on top of a glacier almost 4 kilometers thick. On July the 21st, 1983, the thermometers there registered minus 89.2 degrees Celsius. In Kelvin, that is 184. It is the coldest air temperature ever directly measured on the surface of this planet. At that temperature, exposed human skin freezes in less than a minute. Steel becomes brittle. Diesel fuel turns to slush. Breath exhaled from the mouth crackles faintly in the air, a phenomenon Siberian villagers call the whisper of the stars, because the water vapor in your breath freezes into tiny crystals that collide and hiss as they fall. Satellite measurements have found even lower temperatures on the snow surface in Antarctica, down to about minus 98 degrees Celsius, or 175 Kelvin, in shallow hollows on the East Antarctic plateau, first reported by Ted Scambos of the National Snow and Ice Data Center in 2018. These are the coldest naturally occurring temperatures the surface of Earth has ever been able to produce. And they are, compared to what waits above our heads, still almost unimaginably warm. Consider this. The coldest point on Earth is 175 Kelvin. The coldest point in low Earth orbit in the shadow of the planet is about 120 Kelvin. Already, simply by stepping 300 kilometers upward out of the atmosphere into the shadow of your own world, you have dropped more than 50 degrees below the coldest temperature this entire planet is capable of producing on its own. And that is only the first step. There is one more foundational idea to plant before we begin, and it concerns what cold does to living things. Because every layer of cold we are going to visit is, to a human body, a method of killing. But the methods differ. They are not all the same kind of death. Understanding those differences will change how you hear the rest of this exploration. At around minus 50 degrees Celsius, which your body will never encounter outside a freezer or an Antarctic expedition, the water in your skin cells begins to crystallize. Ice forms inside the cells themselves, shredding their membranes, bursting them open. This is frostbite in its severest form, the kind that kills tissue beyond any hope of recovery. At minus 100 degrees, the effect accelerates dramatically. Muscle fibers shatter, blood vessels rupture. A body dropped into such a temperature, on a long enough timescale, becomes a kind of shattered crystal, its organic structures transformed into brittle ice lattices. But these are temperatures that still exist within the realm of ordinary matter. Water freezes, proteins denature, familiar things happen. Below a certain threshold, though, somewhere around minus 200 degrees Celsius, in the range of 70 or 80 Kelvin, the rules begin to change. At those temperatures, oxygen itself becomes a liquid. Nitrogen becomes a liquid. The very air you are breathing right now would condense into a pale blue pool on the floor. A human body, placed in an environment that cold would not simply freeze. It would become glass. Its cellular structures would become locked in place so thoroughly that the body would take on the physical properties of a ceramic, hard, brittle, capable of shattering if struck. Not a corpse, a sculpture. And we have not even left the neighborhood yet. What you need to carry with you as we begin our descent is this. Every time we drop another few tens of Kelvin, we pass a threshold beyond which yet another category of ordinary matter ceases to behave in ordinary ways. Gases become liquids. Liquids become solids. Solids become superconductors. Quantum effects emerge. At the bottom, near absolute zero, matter itself begins to behave in ways that have no analog in your daily experience. It forms new phases, Bose-Einstein condensates, Fermian seas that exist nowhere in the natural universe except in the coldest places we know how to make. This is why cold is so terrifying once you begin to take it seriously. It is not just a dimmer version of warmth. It is a series of ever stranger regimes of reality, each one more exotic than the last, each one a little further from anything your intuition can grasp. And the first of those regimes begins just above your head, 300 kilometers. That is the altitude at which the International Space Station orbits the Earth. 300 kilometers straight up from wherever you happen to be sitting or lying right now. It takes the station about 90 minutes to circle the planet. In each orbit, it passes through an arc of sunlight and an arc of shadow. Every 45 minutes, the environment outside the station's walls flips between a blazing sunlit hellscape and a frigid dark one. And it is in the dark arcs that we find our first real layer of cold. When the International Space Station enters Earth's shadow, it does not simply become dim. The sunlight cuts out with astonishing abruptness because there is no atmosphere to soften the transition. No twilight, no dusk, no long, slow reddening of the sky. One moment, the solar panels are saturated with light. Next, the sun has vanished behind the limb of the Earth, and the station is in darkness. And in that darkness, the temperature of any surface exposed to space begins to plummet. Consider an aluminum panel on the outside of the station. In sunlight, that panel can reach about 120 degrees Celsius, hot enough to boil water, hot enough to sear flesh. When the shadow arrives over the next 20 or 30 minutes, that same panel will cool to roughly minus 150 degrees Celsius, about 120 Kelvin. And then, 45 minutes later, the sun will reappear and the panel will climb back to its baking daytime temperature. This cycle repeats 16 times a day, every day, for as long as the station stays in orbit. You can imagine what this does to materials over time. Aluminum, steel, solar panel glass, every fitting and fastener on the exterior of the station. All of them expand and contract ever so slightly through a 300-degree swing, 16 times every day. The engineers who designed the station at agencies like NASA and Roscosmos and JAXA had to think very hard about this cycle. They had to choose materials whose thermal expansion coefficients matched closely enough that the structure would not simply tear itself apart over years of flexing. They had to design fluid loops that circulate ammonia through radiators on the outside of the station, shedding waste heat from the interior into the vacuum. They had to design insulating blankets, those golden, crinkled-looking layers you see wrapped around spacecraft, made of alternating sheets of metallized plastic and mesh, specifically engineered to minimize radiative heat transfer in either direction. Everyone knows that space is cold. It is one of those facts you absorb in childhood and never question. It floats around in the general cultural awareness, along with space is dark and space is empty. Everyone knows this. But here is the thing. When engineers design spacecraft, the biggest thermal problem they face is not keeping the vehicle warm. It is keeping the vehicle cool. The sun, in the vacuum of space, without atmosphere to filter it, delivers a relentless 1400 watts of power to every square meter of a spacecraft's sunlit side. That is enough to overheat electronics, boil fuel, and warp structures. Most of the thermal engineering on the outside of a spacecraft is dedicated to shedding heat, not preserving it. The radiators on the side of the International Space Station are not there to warm anything. They are there to dump excess heat into the sky. This is the first apparent simple fact of cold in space that turns out to be more complicated than it seems. Cold is not the immediate enemy. the sun is, and cold only becomes dangerous when the sun disappears. When an astronaut is on a spacewalk and the station crosses into Earth's shadow, their suit has to manage this transition with extraordinary precision. The suit itself is a miracle of engineering, a multi-layered garment whose outer shell reflects sunlight, whose inner layers insulate against both heat and cold, whose internal plumbing circulates cooling water through tubes laced throughout the fabric. In the sunlight, the water carries heat away from the astronaut's body and dumps it through a sublimator that boils ice into vacuum. In the shadow, the heating system switches on, the water flow adjusts, and the suit works to prevent the astronaut from slowly cooling down. Does the astronaut feel the cold? Not in any sudden way. The suit is too well insulated. What they might feel, if the shadow is long enough and their suit's heating is inadequate, is a creeping chill in their fingers and toes, the extremities, the places where warm blood has the hardest time reaching. Some astronauts have reported that on long spacewalks, their fingertips went numb inside the pressurized gloves. Not because the suit failed, because even a suit that works perfectly leaks a small, slow amount of heat into the surrounding vacuum, and given enough time, that small leak adds up. Now extend the thought experiment. Imagine, for a moment, and this is only an imaginative exercise, not a real situation, an astronaut who becomes separated from the station during a nighttime spacewalk. Their tether fails. They drift away. The suit's radio is intact, but the station cannot reach them in time. The sun, on this side of the orbit, is hidden behind the Earth. The astronaut is in the shadows. What happens to them? The first thing to understand is that they do not freeze. Not quickly. Contrary to the imagery in certain films, a human body in the vacuum of space, in shadow, does not instantly turn into an ice sculpture. Remember, there is no air to conduct heat away, no wind. The only way the suit can lose heat is by radiating it, and radiation is slow. In practice, the astronaut would die of suffocation long before cold became their primary concern. Their suit might keep them alive for 6 or 7 hours of oxygen supply. Over those hours, the suit would gradually cool, and the astronaut inside would gradually feel the temperature of their environment drop. But it would be a slow cooling, measured in degrees per hour, not degrees per second. This is the strange, almost cruel fact of cold in low Earth orbit. It does not strike. It waits. It is there, always on the dark side of the planet, a reservoir of frigidity patient enough to eventually drain any heat source you place inside it. But it does so at a pace so measured, so unhurried, that your immediate danger always seems to be something else. Your oxygen, your power, your tether. Cold in this environment is the slow eventuality, not the sudden catastrophe. And yet, the temperature outside an unpressurized spacecraft in Earth's shadow is roughly 120 Kelvin, minus 153 degrees Celsius. That is more than 60 degrees colder than the coldest place ever recorded on Earth. It is cold enough that water vapor freezes on contact with any surface it encounters. It is cold enough that certain plastics become as brittle as glass. It is cold enough that if you placed a cup of warm coffee in a thermally conductive container and set it outside the station, the coffee would not just freeze. The ice itself would continue cooling, down into regimes where ice behaves strangely, where its crystal structure begins to shift into forms your physics teacher never showed you. We think of this layer, the shadow of Earth 300 kilometers up, as the edge of space, the boundary, the place where home ends and the void begins. But it is not really the void. Not yet. It is, in some ways, still a domesticated cold. It is a cold shaped by Earth's geometry, a cold that exists in the rhythm of orbits, cold that flicks on and off every 90 minutes like a light switch. The station passes through it 16 times a day and emerges each time back into sunlight. The astronauts inside, protected by centimeters of aluminum and insulation, barely notice. You will never see this layer with your own eyes, most likely. Very few humans have. But you can, sometimes, on a clear, dark night, watch the International Space Station pass overhead, a bright point moving against the stars, and know that the people inside it are cycling between scorching daylight and cryogenic night 16 times every 24 hours. Their bodies, insulated by their ship, experience none of it. Their ship, designed by engineers who knew exactly what was coming, sheds the heat in sunlight and holds the warmth in shadow. The cold is held at arm's length. The cold is managed. And somewhere, in the shadow beyond the shadow, far from the station, far from any human eye, the same 120 Kelvin is acting on something else. A discarded fragment of an old satellite, perhaps. A fleck of frozen paint chipped off a rocket body decades ago. A nut that floated free of a wrench during some forgotten spacewalk in the 1970s. These objects, too small for anyone to track, are in thermal equilibrium with the shadow side of space. They are cold. They have been cold for years. They will continue to be cold, cycling through sunlight and shadow until someday, long from now, they drift low enough to re-enter the atmosphere and burn up in a flash of heat that would be, for them, the first warmth they have known in decades. Now we pull back. We leave the neighborhood of Earth. We let our altitude climb from 300 kilometers to 300,000, and then to 300 million. We move outward, away from the warmth of our planet, away from the thick protective atmosphere, away from the regular rhythm of shadow and sun. We arrive at a place where the rules of cold begin to shift, where the Earth is no longer a heat source but a distant blue pinpoint, where the sun still shines but shines differently, where the ground beneath our feet is not ground at all, but the scarred grey surface of another world. We arrive at the moon. And here we meet a cold that is not the cold of an orbit. It is the cold of a stationary surface, baked and frozen in turn by a day that lasts 2 weeks and a night that lasts just as long. The moon has no atmosphere. None. Not a trace. Which means that on the moon, every quirk and paradox of cold that we have been slowly building up gets amplified, extended, made unforgiving in ways that Earth's orbit never quite manages. On the sunlit side of the moon, during the lunar day, surface temperatures reach about 120 degrees Celsius, hotter than boiling water. The regolith, the fine dust that coats the lunar surface, bakes at temperatures that would ignite certain organic materials on contact. But then, as the sun sets on the moon, slowly, agonizingly over the course of several Earth days, the temperature begins to drop. And because there is no atmosphere to retain heat and no wind to carry warmth from one region to another, the surface cools with almost nothing to slow it down. By the middle of the lunar night, surface temperatures on the moon's equator fall to about minus 170 degrees Celsius or 100 Kelvin. Colder than anywhere in low Earth orbit. Colder than almost anywhere on Earth, even in the most extreme Antarctic winter. And this is just the equator. Move toward the poles and the cold deepens. At the lunar South Pole, there are craters that have never in billions of years seen sunlight. Their rims rise high enough that the low-angle sunlight at the pole always falls just past them. Their interiors lie in permanent shadow. Inside these craters with names like Shackleton and Faustini, and shoemaker named after polar explorers and planetary scientists of the 20th century. The temperatures fall to a range that genuinely begins to approach the cold of deep space. NASA's Lunar Reconnaissance Orbiter, launched in 2009, carried an instrument called Diviner, led by principal investigator David Page at UCLA, which measured temperatures inside some of these permanently shadowed regions as low as 25 Kelvin, 25 degrees above absolute zero, minus 248 degrees Celsius, 25 Kelvin. Hold that number in your mouth for a moment. Feel how close it sits to the floor of the universe, only 25 degrees up from the absolute bottom. The coldest naturally occurring place in the inner solar system, just a few 100,000 kilometers from your window, is 900 miles inside a crater on the moon. These are called the PSRs, permanently shadowed regions, and they are some of the strangest places in the solar system because they are archaeological sites. Anything that has ever drifted into them, a water molecule from a long-dead comet, an organic compound from an ancient asteroid impact, a hydrogen atom from the solar wind, has, in many cases, simply never left. The temperature is too low for these volatiles to sublimate back into vapor. They arrived, they froze, they stayed. The floor of Shackleton Crater may contain water ice that has been sitting undisturbed since before the Earth's oceans formed. Ancient frost, preserved by a cold so patient it has outlasted the invention of multicellular life. You might picture this scene in your mind and picture it wrong. You might imagine a cold place the way you imagine the Antarctic, a bright white landscape of blowing snow. But Shackleton Crater does not look like that. It is black. It is sealed in a darkness so complete that for most of the time humans have been measuring it, we did not know for certain what was inside. Sunlight does not enter. Earthlight does not enter, because the crater faces the wrong way. The only illumination is the faint glow of distant stars and, occasionally, the weak infrared signature of rocks at 100 and something Kelvin, emitting the ghost of their own warmth. An astronaut standing inside Shackleton with the right sensors could watch the walls of the crater glowing faintly in infrared, like a slowly dying fire, a fire so cold that to human eyes it would look like perfect black. Astronauts may soon stand there. The Artemis program, the American-led effort to return humans to the moon, has targeted the lunar South Pole precisely because of these cold traps. The water ice locked inside them represents the most accessible reservoir of hydrogen and oxygen in the inner solar system. Raw material for breathing air, for drinking water, for rocket fuel. But retrieving that ice means sending humans and machines into temperatures that would, unprotected, kill them in seconds. No Apollo mission ever went near these temperatures. The Apollo astronauts landed on the lunar dayside in relatively temperate regions, and they were only on the surface for a few hours at a time. Artemis is a different proposition entirely. Artemis is trying to stay. Artemis is trying to put a human boot down on ground that has not been above 100 Kelvin since long before there was such a thing as a boot. Some researchers argue the engineering challenges of operating at such temperatures are manageable with existing materials. Heated boots, insulated suits, heated rovers, mission profiles designed to move in and out of shadow on carefully timed cycles. Others argue the thermal problems are far harder than NASA has publicly admitted, that batteries simply do not work at 25 Kelvin, that lubricants freeze, that seals contract until they no longer seal, that the cycle of cold to warm to cold over and over will fatigue every material you send there. Both sides have good arguments. We will find out, probably within this decade, who was right. But that is the surface question. The deeper question, the question that matters for our descent, is what cold of this depth actually is. And to understand that, we need to take a moment and think about what happens to matter at 100 Kelvin. At 100 Kelvin, oxygen is a pale blue liquid, denser than water. Nitrogen is a colorless liquid that boils at 77 Kelvin, barely 23 degrees below where we are standing. If you spilled a cup of liquid nitrogen on the floor of Shackleton crater, it would sit there, placidly, without boiling away, because the crater floor is colder than nitrogen's boiling point. Think about what that means. Think about the rooms in hospitals where liquid nitrogen is stored in thick-walled dewars, where technicians wear heavy gloves to handle it, where a splash on bare skin would cause instant frostbite. Imagine standing somewhere so cold that that liquid simply sits, untroubled, at ease, because the environment around it is even colder than it is. Carbon dioxide at 100 Kelvin is a hard white solid, dry ice, the kind that smokes and hisses in your hand. Methane is a liquid, and below 90 Kelvin it freezes solid. All the gases you breathe, all the gases that make up the atmospheres of the inner planets, are at this temperature no longer gases. They are solids and liquids settled onto the ground, patient, accumulating. A human body placed unprotected on the floor of Shackleton crater would not experience the slow, gentle cooling of an astronaut in low Earth orbit. The radiative heat loss would be more severe because the background is colder, and the body would be in contact with a solid surface, regolith at 100 Kelvin, which would conduct heat away through the soles of the feet at a rate that would produce serious tissue damage within minutes. Not the gradual hours of orbital cold, actual, tangible freezing, fast enough to notice, not fast enough to save you. This is the second layer, the cold of the lunar night, the cold of the permanently shadowed pole, a cold that finally begins to resemble the cold of your intuitions, a cold that can hurt you, that can kill you in a timescale your nervous system can register. And yet, it is still, cosmically speaking, a minor cold. We have descended from your skin at 310 Kelvin to the air outside at 260, to the coldest place on Earth at 175, to low Earth orbit shadow at 120, to the deepest lunar craters at 25. 25 Kelvin is cold, but 25 Kelvin is still nearly 10 times warmer than the cold we are heading toward. Zoom out once more. Leave the moon behind. Push outward through the orbit of Mars, through the asteroid belt, past the colossal banded cloudscape of Jupiter, past the thin golden rings of Saturn. The sun, from here, is beginning to shrink. On Earth, the sun is a disk in the sky. At Saturn, 10 times farther out, the sun is a bright star, still the brightest object in the sky, but no longer something you could confuse with the source of a planet's warmth. The solar constant, that 1400 watts per square meter that defines Earth's sky, has fallen by a factor of 90. A solar panel that powers a house on Earth would, at Saturn's distance, barely run a light bulb. Keep going, past Uranus, past Neptune, past the orbit of Pluto, where the sun is now just a very bright star and nothing more. And then beyond, into the Kuiper Belt and the Oort cloud, the frozen outskirts of our solar system, where ancient comets drift on orbits so long they have not completed a full revolution since the pyramids were built. The temperature out here, in the interstellar adjacent regions of our own solar system, hovers at around 10 Kelvin on unilluminated surfaces. 10 Kelvin, 10 degrees above absolute zero. This is the temperature of the outer surfaces of distant comets. This is the temperature of the solid methane that coats some trans-Neptunian objects. This is a cold in which not just familiar gases, But water ice itself begins to behave as though it was stone, harder than granite, resistant to sublimation, capable of holding its shape for billions of years. Here is a number that, when you first encounter it, sounds like an error. Water ice, at 10 Kelvin, has a hardness comparable to bedrock. It is nothing like the ice in your freezer, which is a soft, manipulable material that melts at the touch of a warm hand. Cosmic ice at 10 Kelvin is a structural material. Entire moons are made of it. Europa and Enceladus, Triton and Titania have surfaces made of water ice that behaves, under those temperatures, more like basalt than anything you would recognize as ice. You could build a house out of it. You could build a bridge out of it. If you could somehow bring a slab of such ice back to Earth without warming it, it would be one of the hardest natural materials you had ever touched, until it warmed, and then it would turn, dramatically, disappointingly, into ordinary water. There is a cosmic irony in this. Ice is a wimp on Earth and a titan in space. The same molecular structure, the same two hydrogen atoms bonded to one oxygen atom, behaves like completely different materials depending on how much thermal energy is available to rattle its lattice. At 270 Kelvin, the lattice rattles so energetically that the slightest additional warmth breaks it apart. At 10 Kelvin, the lattice barely moves. The bonds hold, the structure endures. This is one of the recurring themes of the descent we are undertaking. As we go colder, matter becomes more committed, more rigid, more unwilling to change. Things that were fluid at higher temperatures freeze. Things that were frozen become harder. Things that were hard become almost geological. The universe, at low temperatures, is a universe of long duration. Things last. They last because nothing has enough energy to rearrange them. 10 Kelvin, however, is not the baseline of interstellar space. Objects this cold are this cold because they are close to the sun, in some distant sense, close enough that the sun's dim light still warms them slightly above the background. Move further out, away from even that faint warming, and you drop lower still. Leave the solar system entirely. Enter the vast dark between the stars, and you arrive, finally, at the famous number. The number Penzias and Wilson discovered in their antenna in 1964. The number that every spacecraft probe eventually converges on when it travels far enough from any heat source. 2.7 Kelvin, interstellar space, the true deep. The place where only the cosmic microwave background shines, and shines equally in every direction, with the faint, lingering warmth of the Big Bang cooled over 13.8 billion years into near silence. We are now, cosmically speaking, standing on the bottom step of the temperature ladder. Anything we have talked about so far sits above this point. Any object in the universe, left alone, not heated by a star or a radioactive core or a friend's fire, will eventually cool to 2.7 Kelvin and no lower. This is where the universe rests. This is where the universe wants to be. And remember what we said earlier. This is not some quirk of average conditions. This is the floor the CMB sets, everywhere, inescapably. The vast majority of volume in the observable universe sits at this temperature. Let's dwell here for a while, because this is where cold stops behaving like cold and starts behaving like something else. At 2.7 Kelvin, any surface you could imagine, a rock, a metal plate, a human hand, would, if brought to thermal equilibrium with its surroundings, become almost impossible to distinguish from the vacuum itself. It would emit so little infrared radiation that detecting it would require instruments sensitive enough to count individual photons. It would be, in the most literal sense, dark. Not dark as in shadow, dark as in not producing light at any wavelength the human eye or most human instruments could detect. A rock at 2.7 Kelvin is cooler than the cooling coils of the deepest cryogenic refrigerator ever built on Earth. It is matter at the bottom. The James Webb Space Telescope, launched in 2021 under the leadership of project scientists, including John Mather, who had already won the Nobel Prize in 2006 for his work measuring the spectrum of the cosmic microwave background, had to solve a brutal thermal problem. To detect the faint infrared light from the earliest galaxies, its primary mirror and instruments needed to be colder than the objects they were trying to see. The telescope is parked at the second Lagrange point, about 1.5 million kilometers from Earth, in a location where a 5-layer sunshield the size of a tennis court can permanently block the combined heat of the Sun, the Earth, and the Moon. The cold side of that sunshield sits at around 40 Kelvin. The telescope's most sensitive instrument, the mid-infrared instrument, or MIRI, has to be cooled even further, down to about 7 Kelvin, using a dedicated cryocooler. The entire design of the telescope is a monument to the difficulty of actually reaching the cold that the universe offers for free almost everywhere. Almost everywhere. But not quite, because 2.7 Kelvin is the baseline, and the baseline is cold, but the baseline is not the floor. There are places, rare places, where nature has managed to go colder still. Places where a cloud of gas, expanding rapidly into a vacuum, has drained its own thermal energy below the cosmic background. Places where the universe's average temperature is not the minimum temperature. Places where, for a brief geological moment, a pocket of matter sits in a state colder than the glow of the Big Bang itself. The most famous of these is a strange object about 5,000 light-years from Earth in the constellation Centaurus. It is a dying star surrounded by an outflow of gas, a kind of pre-planetary nebula, and it carries a name that sounds too whimsical for what it actually is. It is called the Boomerang Nebula, and it is, by the best measurements astronomers have been able to make, the coldest naturally occurring place known in the universe, roughly 1 Kelvin, 1 degree above absolute zero, colder than the cosmic microwave background, colder, in fact, than anywhere else we have ever detected with a telescope. A pocket of natural cryogenic cold floating in the darkness between the stars, created not by some exotic mechanism, but by the simplest process imaginable. A gas expanding very rapidly and cooling, like air rushing out of a pressurized can, but on a vastly larger scale and with nothing to resupply its warmth. We will come back to the boomerang. We are going to spend time there, because it is a place that rewards patient attention. But before we go, let us take a final measurement of where we are in our descent. We started at the warmth of your body, 310 Kelvin. We stepped outdoors into winter, 260. We visited the coldest place on Earth, 175. We traveled to low Earth orbit's shadow, 120. We descended into a lunar crater where sunlight had not fallen in 4 billion years, 25. We crossed the outer solar system and found surfaces at 10. We went out into the interstellar dark and found the baseline of the universe, 2.7. And we have one more layer to descend, one more layer of natural cold, stranger than anything above it, before we reach the regime where cold is no longer natural, where cold, the last sliver of it, is produced only in human laboratories, under conditions so fragile and so difficult that maintaining them is a quiet act of defiance against the architecture of the universe itself. Let us begin the approach to the boomerang. Let us take our time. Let us understand first what it means for something to be colder than the universe. You might think intuitively that nothing can be colder than the background, that if space itself sits at 2.7 Kelvin, anything you place in it must also eventually warm to 2.7 Kelvin. And that is, in the long run, correct. Any object in thermal equilibrium with the cosmic microwave background will sit at 2.7 Kelvin. The universe tends toward that temperature the way water tends toward a level surface. But here is where a piece of simple physics opens a door that most people do not realize is there. Equilibrium takes time, a lot of time. And during the time it takes to reach equilibrium, it is possible, under specific circumstances, for an object to be temporarily colder than its surroundings. Not forever, but for long enough to matter. For long enough, sometimes, that human instruments can detect the difference. The circumstances that produce such pockets of below-background cold all involve rapid expansion. When a gas expands, it cools. This is the principle behind every refrigerator ever built. Compress a gas, it warms. Let it expand, it cools. The faster the expansion, the greater the cooling. And if a gas expands fast enough into a sufficiently empty space, its temperature can drop below the ambient temperature of its environment before it has time to absorb enough radiation to warm back up. In a laboratory on Earth, we use this principle to create temperatures colder than outer space. In space, the same principle sometimes creates natural cold pockets. Stellar winds expanding into the interstellar medium, outflows from dying stars, certain rare configurations of gas dynamics that produce what physicists call adiabatic cooling, cooling by expansion alone without heat transfer to anything else. The Boomerang Nebula is the most extreme example of this that has ever been found. At its heart is a dying star, probably a red giant in the late stages of its life, and for reasons we still do not fully understand. That star has been shedding its outer layers at an extraordinarily high velocity, around 160 kilometers per second. That is about 10 times faster than the outflow from most similar dying stars. The gas is being flung outward into the vacuum so rapidly and into a region so nearly empty that it cools as it goes, and it cools much faster than the cosmic microwave background can warm it back up. The result is a bipolar outflow, a pair of symmetric lobes of gas expanding in opposite directions, roughly perpendicular to the star's equator, in which the gas temperature has dropped to about 1 Kelvin. 1 degree above absolute zero, 1.7 degrees colder than the cosmic microwave background. A region of space, roughly a light year across, that is the coldest place humanity has ever measured. The boomerang was discovered, in a sense, twice. It was first noticed in visible light by Keith Taylor and Mike Scarrett in 1980, who gave it its name because of its bent, wing-like shape in early images. But the true nature of its cold was not understood until the 1990s, when radio astronomers Raghvendra Sahai and Lars-Åke Nyman, working with the Swedish ESO submillimeter telescope in Chile, made careful measurements of the nebula's absorption of the cosmic microwave background. Sahai and Nyman published their findings in 1997, establishing the boomerang as colder than the background itself. More recent observations, particularly with the Atacama Large Millimeter Array in Chile since around 2013, have refined those measurements and confirmed to the satisfaction of most astronomers that this is indeed the coldest natural place currently known. Picture it. Really try. Picture a pocket of space, 5,000 light-years from here, light-years across, where the temperature is colder than the background temperature of the universe itself. Picture the fact that this pocket is not stable. It is an ongoing event, a slow cascade of cooling gas that will, over the next few thousand years, gradually warm back up to equilibrium as the cosmic microwave background soaks into it. Picture the fact that at the center of this pocket is a dying star, still fusing elements, still producing light, sending out radiation that, at the outer edges of the nebula, is insufficient to warm the gas past the cold its own expansion is producing. There is something almost religious about the boomerang, if you sit with it long enough. A star is dying. In its death throes, it is flinging out its own atmosphere into the void, and those exhaled layers in their flight become colder than the universe they fly into. The star's final breaths are quite literally the coldest thing we know of. A stellar exhalation so forceful that it outruns the warmth of the Big Bang. Let us stay inside the boomerang a little longer, because what happens to matter at 1 Kelvin is worth understanding before we move on. At 1 Kelvin, almost nothing you think of as chemistry can occur. Chemical reactions require activation energy, a threshold of thermal motion that allows molecules to collide hard enough to rearrange their bonds. At a temperature of 1 Kelvin, most molecules are not moving fast enough to react with each other at all. The gas in the boomerang is, in a profound sense, frozen in time. Molecules drift past each other without interacting. Atoms that should combine do not combine. Chemistry, the great ongoing conversation of matter with itself, has fallen silent. And yet the boomerang is not empty. It contains, according to the ALMA measurements, significant amounts of carbon monoxide, dust grains, complex molecules that formed in the warmer layers closer to the dying star and have been flung outward into the cold. These molecules are preserved in some sense in a chemical amber. They are not reacting. They are not decaying. They are simply drifting at 1 Kelvin, waiting for something to warm them back up. What would it feel like to stand in such a place? Setting aside for a moment the question of how you would survive, you would not. What would your senses actually register in the moments before they failed? You would see, first, the dying star at the center of the nebula, not as a brilliant point, but as a diffuse, distant glow, reddened and veiled by the dust of its own outflow. Around you in every direction, the nebula itself would appear almost transparent, a gas so thin that your gaze would pass through light years before encountering anything dense enough to scatter the light. The stars of the Milky Way, far beyond the nebula, would be visible through its gossamer edges, shining with a hardness that only the vacuum can produce. You would feel immediately the pull of the cold, not as a sting or a bite, the way you would feel it on Earth, but as a vast, slow draining. Heat would begin to leave your body in every direction at once, radiating off your skin as infrared light into the 1 Kelvin darkness. You would feel cold the way you feel cold in a dream, a cold that is everywhere and nowhere, that has no source and therefore no escape. And then your lungs, your blood, your cells would begin to change in ways we already described earlier in this journey. You would not last long. You would not need to. But the boomerang itself would not notice you. It would continue its slow expansion, its gas molecules drifting outward at their supersonic velocity, their temperature holding at just above absolute zero for as long as its mechanism continues to run. Another few thousand years, perhaps. And then, one way or another, the cooling would cease. The cosmic microwave background would reassert itself, and the boomerang would warm back up to 2.7 Kelvin, like everything else in the universe does eventually. Now, a question. If 1 Kelvin is the coldest natural temperature we know of, what about unnatural ones? What about the cold humans themselves can produce? This is where the story takes its final turn and begins to descend into regions that have no cosmic counterpart. where the very word cold begins to lose its ordinary meaning. Since the late 19th century, physicists have been racing each other to lower and lower temperatures, each one pushing a little further toward absolute zero, each one discovering new phenomena along the way. In 1908, the Dutch physicist Heike Kamerlingh-Onnes became the first person to liquefy helium, reaching a temperature of about 4 Kelvin, colder than interstellar space, though Onnes did not know that, because the cosmic microwave background had not yet been discovered. Onnes won the Nobel Prize in 1913 for his work, and more importantly, he opened the door to an entirely new field of physics. 3 years later, in 1911, while studying the electrical resistance of mercury at these new temperatures, Onnes discovered something nobody had predicted: superconductivity, the disappearance of electrical resistance in certain metals. Electrons, cooled sufficiently, begin to flow through a conductor without losing energy to collisions with the atomic lattice. An electric current, once started in a superconducting loop, will continue, in principle, forever, with no power source. This is not a metaphor. This is not an exaggeration. There are currents running in laboratory, superconducting magnets today that have been running continuously for decades, losing no measurable energy. The only thing sustaining them is the cold. Below 4 Kelvin, other phenomena emerge. Liquid helium itself, below about 2.2 Kelvin, becomes a superfluid, a liquid with zero viscosity, able to flow through the smallest cracks, capable of climbing the walls of its container, behaving in ways that violate every common-sense intuition about what liquids are. Superfluid helium will, left to itself, slowly creep up the sides of a beaker and drip over the rim, because its zero viscosity allows it to flow through microscopic films at the surface. This is not science fiction. This is what helium does when you cool it to within 2 degrees of absolute zero. Matter, at these temperatures, does not merely sit still. It behaves strangely. In 1995, physicists Eric Cornell and Carl Wieman at the University of Colorado, working with atomic physics techniques developed in collaboration with Wolfgang Ketteler at MIT, achieved a temperature of about 170 nanokelvin, that is, 170 billionths of a degree above absolute zero. At this temperature, a small cloud of rubidium atoms entered a previously only theoretically predicted state of matter called a Bose-Einstein condensate, in which thousands of atoms merge into a single quantum entity, all behaving as though they were the same particle. Cornell, Wieman, and Kettel shared the Nobel Prize in 2001 for this work. They had created, in a laboratory, a temperature roughly 10 million times colder than anywhere in deep space, and the race has continued. Modern laboratories routinely produce temperatures below 1 nanokelvin, 1 billionth of a degree above absolute zero. MIT researchers in 2003 reached about half a nanokelvin. More recent experiments using sophisticated laser cooling and evaporative cooling techniques have pushed even lower into the picokelvin regime, trillionths of a degree. In 2021, a team led by physicists at Leibniz University Hanover and the University of Bremen reported an effective temperature of about 38 picokelvin in a rubidium condensate during a brief freefall experiment at the Bremen Drop Tower. 38 trillionths of a degree above absolute zero. These numbers, by this point, have probably lost all meaning to you. That is appropriate. They should. Because we have passed beyond the point where human intuition can follow. A temperature of 38 picokelvin is not merely cold. It is not merely very cold. It is a temperature so far below anything in the natural universe that, to the universe's perspective, it is almost a kind of hallucination. There is nowhere in the entire observable cosmos outside of human laboratories where such temperatures exist. Humans, in small glass chambers, in basements in Germany and Colorado, and Massachusetts and Tokyo, have created the coldest matter that exists anywhere. The coldest locations in the universe, as far as we know, are on Earth. Surrounded by a cosmos that averages 2.7 Kelvin, a single species, in a handful of laboratories, has dug holes 1 billion times deeper than the natural floor. Pause on that for a moment. There is something genuinely vertiginous about it. The warmest places in the universe are inside stars, where fusion cooks matter at millions of degrees. The coldest places in the universe are inside rubidium vapor traps on your own planet. You live in a world that contains both extremes, separated by walls and kilometers and careful engineering. Everywhere else, the universe is cold. Only here, on Earth, has anyone thought to push back. But pushing back is hard. Maintaining a temperature of 38 picokelvin for more than a fraction of a second is essentially impossible. Any stray photon, any vibration, any hint of thermal radiation, any contact with a surface, any gravitational disturbance will warm the sample. The deepest cold humanity has achieved is not a stable state. It is a transient event, a fleeting moment, a whisper that exists for a fraction of a second before being erased by the relentless thermal pressure of the universe. And this leads us, inevitably, to a question that has been hovering in the background of everything we have discussed so far, a question whose answer is going to turn the entire exploration inside out. What is temperature, really? What is this thing called cold at the deepest level? We said at the beginning that cold is the absence of motion, that heat is the vibration of atoms, and cold is the slowing of that vibration. And that is true as far as it goes. But it is not the whole truth, because as you approach absolute zero, an entirely different kind of physics takes over, and the simple picture of atoms jittering more or less vigorously begins to break down. Quantum mechanics asserts, through a principle called the Heisenberg uncertainty principle, that a particle cannot simultaneously have a perfectly defined position and a perfectly defined momentum. If an atom were perfectly still, its momentum would be perfectly defined, exactly zero, and its position would become, in principle, completely uncertain, smeared across infinite space. This is not physically possible, and so, even at absolute zero, atoms cannot actually stop moving. They retain a minimum amount of motion, called zero-point motion, which is a kind of quantum jitter built into the fabric of matter itself. This is why you cannot reach absolute zero. It is not simply that it is practically hard. It is that absolute zero is a theoretical concept that matter at the quantum level cannot actually occupy. The floor of temperature is not a place you can stand on. It is a limit you can approach, asymptotically, forever. And this raises a series of questions that have not been resolved, questions that sit at the edge of modern physics, questions whose answers may reshape our understanding of what the universe is. What does it mean to be cold in a quantum regime? Does temperature even make sense as a concept when applied to a single atom? How do we reconcile the classical picture of heat as motion with the quantum picture of zero-point energy? Is there a deeper floor below temperature itself, some more fundamental quantity that temperature is only a surface expression of? And if cold is the absence of motion and motion is energy and matter are interchangeable, then is cold at some level the absence of matter itself? Hold these questions. We are going to return to them. But first, we need to visit one more place, one more layer, because we have talked about the coldest place in the natural universe, and we have talked about the coldest place in the universe overall, which is in a laboratory on Earth. But we have not yet talked about the coldest place the universe will ever produce, given infinite time. We have not yet talked about the future. We have not yet talked about the heat death. Let us take a breath. Let us pause here, on the edge of something even colder than the boomerang, even stranger than a rubidium condensate. We are going to step now out of the present and into the deep future of the cosmos. And we are going to ask what the temperature of the universe will be when all of its stars have gone out, when all of its warmth has drained away, when nothing is being actively heated anymore by fusion or radioactive decay or gravitational compression or any of the other mechanisms that currently keep the average temperature of matter elevated above the background. The answer is not 2.7 Kelvin. The answer is not 1 Kelvin. The answer is colder than that. Dramatically, profoundly, incomprehensibly colder. Because the cosmic microwave background is itself cooling. The universe is expanding, and as it expands, the wavelengths of the photons that make up the CMB are being stretched. Longer wavelengths correspond to lower energies. Lower energies correspond to lower temperatures. The CMB, which is now at 2.7 Kelvin, was about 3,000 Kelvin when it was first released, 380,000 years after the Big Bang. It has cooled by a factor of roughly 1,000 since then, as the universe has expanded by a factor of roughly 1,000. And it will continue to cool. It will keep cooling forever as the universe keeps expanding. 100 billion years from now, the CMB will have cooled to roughly a few thousandths of a Kelvin. A trillion years from now, it will be colder still. By the time the last stars have burned out, roughly 100 trillion years from now, the CMB will have cooled to temperatures that are, by any reasonable metric, effectively zero. And the universe will be, for the first time in its history, genuinely cold. Colder than the Boomerang Nebula is now. Colder than anything nature has so far produced outside of a laboratory. And it will keep cooling, because the expansion is not stopping. There is no force we have yet identified that will reverse it. The universe, as far as the best observations can tell us, is going to keep expanding forever at an ever-increasing rate. And as it expands, everything in it is going to keep cooling forever toward a temperature that approaches but never quite reaches absolute zero. This is the scenario called heat death. And it is, in some ways, the true end point of our descent. It is the state toward which the entire universe is falling. Not the cold of a particular place at a particular time, but the cold of everything, everywhere, in the limit. The physicist Freeman Dyson, in a famous 1979 paper titled Time Without End, explored what would happen to intelligent life in such a universe, how long it could persist, how it could slow its metabolism to match the cooling environment, whether there was any way to survive indefinitely as the ambient temperature approached zero. Dyson's calculations, and the follow-up work by other physicists since then, have generally concluded that under certain assumptions, consciousness might be able to persist indefinitely, even as the universe cools, by running ever more slowly, thinking ever more slowly, using ever less energy, a ghost of intelligence flickering across a cold so deep that a single thought might take 1 billion years. Under other assumptions, no such persistence is possible. Under still other assumptions, the ones that seem to be favored by current observations of cosmic expansion, the universe is not merely cooling, but accelerating. And in that case, all structure will eventually be torn apart by the expansion itself. And there will be nothing left to cool or to be cooled, only an empty, dark, almost unimaginably cold space expanding into itself forever. Nobody knows which of these scenarios is correct. Some researchers favor the eternal slow cooling of a more classical heat death. Others favor the accelerating expansion picture, sometimes called the Big Rip. Still others entertain the possibility that our current understanding of cosmic expansion is incomplete, that there may be effects we have not yet measured, that the universe might in some sense recover from its current direction of travel. We do not know. But we do know this: the arrow points down. Whatever the exact shape of the future, the temperature of the universe is heading toward absolute zero, and nothing we currently understand can stop that descent. The average cosmic temperature was millions of degrees when the universe was young. It is 2.7 Kelvin now. It will be picokelvin, attokelvin, zeptokelvin in the deep future. And it will keep going, asymptotically, toward the floor. You have lived your entire life inside a warm anomaly, on a warm planet, in a warm time, in a universe whose fundamental tendency is to grow colder. Your experience of temperature is an artifact of a transient, improbable circumstance. The stars will go out, the planets will cool, the warmth that currently permits your existence is a bubble, and the bubble is shrinking. And now we have arrived at the place where the exploration has to turn, because we have so far been cataloging cold, laying out its layers, measuring its depths, naming its extremes. But there is a deeper question, a more disturbing question, that all of this cataloging has been slowly building toward. Why does the universe tend toward cold? Why is cold the destination and warmth the anomaly? Why does the arrow of thermodynamics point only one way? Why is it that every star, every galaxy, every living thing, every thought, every moment of warmth we have ever experienced is a temporary reversal of a cosmic tendency that is, in the long run, inexorable? Why does entropy increase? This is the question at the heart of everything we have covered. And it is a question that physics has not fully answered. There are hypotheses, there are models, there are beautiful mathematical frameworks. But at the deepest level, the reason the universe tends toward disorder and cold is not something we fully understand. It is something we observe. It is something we measure. It is something we can write equations for. But the underlying why remains, even after centuries of work, elusive. Let us ask it directly. If the laws of physics are, in their microscopic formulation, time-symmetric, meaning that they look the same whether you run them forward or backward, then why does the universe appear to run only forward? Why does heat flow from hot to cold and never the other way? Why do coffee cups cool but never spontaneously warm? Why does cosmic history have a beginning? And why does it seem to have an ending? And why do those two endpoints differ so dramatically in their character? The standard answer involves something called the initial condition of the universe, the claim that the Big Bang produced a very low entropy state, and that the subsequent history of the universe has been the gradual unspooling of that initial low entropy state into progressively higher entropy configurations. Heat flows from hot to cold because there were more hot places than cold places at the beginning, statistically speaking, and the universe is still, in a sense, equilibrating. But this answer only pushes the question back one step. Why did the Big Bang produce a low entropy state? Why did the universe begin in a condition that permits the arrow of time to exist at all? Why, out of all possible initial conditions, did the universe choose this one, the one that leads inevitably to cold? Here is the strange thing. We do not know. We genuinely do not know. Some of the best cosmologists in the world, people like Sean Carroll at Johns Hopkins and Roger Penrose at Oxford, have spent decades trying to answer this question, and their best proposals remain speculative. Penrose, who shared the Nobel Prize in 2020 for his work on black holes, has argued that the low entropy of the early universe is a profound cosmic mystery, possibly requiring entirely new physics to explain. Carroll has explored the possibility that our universe is part of a larger multiverse in which entropy fluctuates, and that we happen to live in a region where it is currently increasing. But this, too, is speculation, not established science. The honest answer is that the tendency toward cold is the most fundamental fact about the universe, and we do not know why it is true. And here, we reach the pivot that reframes every layer we have descended through. Everything we have looked at so far, the winter morning, the lunar crater, the Boomerang Nebula, the rubidium condensate, the heat death of the universe, is not a series of isolated cold places. It is a single pattern expressed at different scales. The universe is running down. Everything we have visited is a snapshot of that running down process, a photograph of entropy in various stages of completion. The cold we have been mapping is not many different colds. It is one cold, one direction, one inexorable slide from warmth into silence, caught at different moments in its unfolding. And the question that should stop you in your tracks, that should shift the ground beneath every assumption you have carried into this exploration, is this. What if cold is not the opposite of warmth, but warmth is a local interruption of cold? What if the default condition of the universe is not something in between hot and cold, but simply cold, and every fire that has ever burned, including the fire in your chest, is a temporary deviation from that default? What if the whole of cosmic history, from the Big Bang to the last proton decay, is best understood as a single process of cooling? A process in which warmth is not an achievement of the universe, but a transient flicker on the way to the final permanent dark? What if you are not a warm being in a cold universe, but a brief, improbable, self-sustaining hotspot in a cold that was here before you arrived and will still be here, quietly, patiently, after the last star has gone out? Can temperature itself be considered a kind of time? When we say a region is 2.7 Kelvin, are we not really saying something about where that region sits in cosmic history, how far along the process of entropy increase it has traveled? A place at 3000 Kelvin is, by this way of thinking, not merely hotter, it is earlier. And a place below 2.7 Kelvin is, in some sense, later than the universe itself, colder than the average history has yet achieved. Does this mean the Boomerang Nebula, at 1 Kelvin, is a region in which time, thermodynamically speaking, has run ahead of the rest of the cosmos? Is it a small pocket of the deep future, embedded in the present? Is it a place where the heat death has, locally, already begun? And if so, what does it mean to stand, hypothetically in imagination, inside such a place? What does it mean to be in a region of space-time that is, in thermodynamic terms, further along in its history than the universe around it? Would it feel, somehow, older? Would it feel like being in a memory rather than in a moment? There are no firm answers to these questions. And here is where we must admit something plainly, because this whole exploration has tried to be honest about what we know and what we do not. We cannot know what the deepest cold actually feels like, because no creature that feels anything has ever existed at such temperatures. We cannot know, as a matter of physical principle, whether our framework of temperature, an idea invented by warm creatures on a warm planet to describe the small range of conditions in which warm creatures can exist, extends all the way to the bottom in the way we imagine it does. It may be that at sufficiently low temperatures, our very concepts begin to misfire. that the word cold loses its meaning somewhere on the way down, that there is a threshold below which the question, how cold is it, does not have an answer we are equipped to recognize. Stand on a hilltop on a clear winter night. Let the air around you settle. Let your eyes adjust slowly to the dark until the stars that were invisible at first begin to emerge, one by one, and then by the thousands, scattered across a sky that is itself, you now understand, at a temperature far colder than anything your body will ever touch. Stay there. Do not move. Do not rush. Let the cold of the night air settle around you, -10 perhaps, if it is a truly cold night, which is to say 263 Kelvin, which is to say unimaginably warm by any cosmic standard. You are standing inside a thin sheath of warmth wrapped around a small rocky world, looking up into a dark that stretches billions of light years in every direction. And almost all of that dark is colder than the cup of hot coffee you had this morning by almost 300 degrees. The stars look hard. Have you ever noticed that? On the coldest nights, when the air is driest and the humidity lowest, the stars seem somehow sharper, as though they had been cut from metal and set into the sky. This is, in part, an optical effect. Less water vapor in the atmosphere means less scattering of their light. But it is also, in some deeper sense, perceptually accurate. Each of those points of light is a fire whose warmth has traveled, in some cases for thousands of years, across a cold so vast that the light itself has been slightly cooled in its passage. Every photon from every star has been shifting, imperceptibly, into longer wavelengths as the universe has expanded around it. The light that reaches your eyes is, in a literal sense, a slightly older, slightly colder version of the light that left those stars. You are seeing the cold written into the light itself. Picture, now, a single photon from the cosmic microwave background. One of the quadrillions that pass through your body every second, unnoticed, undetected, because your body is not tuned to their wavelength. That photon was created almost 14 billion years ago, when the universe was about 3,000 degrees Kelvin and filled with a hot plasma of ionized gas. At that moment, when the universe had cooled enough for electrons and protons to combine into neutral hydrogen, the photon was released. It began its journey. 14 billion years of travel, 14 billion years of flight through an ever-expanding, ever-cooling cosmos. During that flight, the wavelength of the photon stretched, its energy dropped. Its temperature, if we can speak of a single photon as having a temperature, fell from something comparable to the surface of a star to something comparable to the deepest natural cold in the universe. When it reached you tonight, standing on your hilltop, it was 2.7 Kelvin. It has been cooling, alone, for longer than there have been continents on Earth, longer than there have been fish in the oceans, longer than there has been any Earth at all. And tonight, one of those photons ended its journey by striking your skin. There are, by the way, about 400 of these photons passing through every cubic centimeter of space around you at all times. You are swimming in an ocean of them. The room you are in, the bed you are lying on, the air above your head is saturated with the cooled radiation of the Big Bang. You are bathed in the cold. You have always been bathed in the cold, and your body, with the patient work of its metabolism, has been holding a 300-degree temperature differential against that cold for every second of your life. Every breath you take warms a small amount of air inside you before releasing it, slightly cooler, back into the world. Every heartbeat drives warm blood through the cold periphery of your extremities. Every cell in your body is, at this very moment, running chemical reactions that produce heat as a byproduct. And that heat is constantly leaking outward, off your skin, into the room, into the atmosphere, into space, eventually, where it joins the accumulating reservoir of thermal radiation that is pushing the universe, atom by atom, photon by photon, a few nanoseconds closer to equilibrium. You are a small, warm rebellion against a cold inevitability. And the rebellion is magnificent. It is the most improbable thing about you. Not your intelligence, not your memories, not your relationships. Simply the fact that your body, against the grain of cosmic history, continues to hold its temperature, continues to burn, continues to insist that here, in this one specific location, for this one specific moment, the arrow of heat flow reverses. Here, briefly, warmth is not draining away, but being actively generated. Here, briefly, the universe's slide into cold is being pushed back. Every living thing you have ever met is doing the same thing. Every cat curled on a sunny windowsill. Every bird hunched against a winter wind. Every fish swimming in the cold, dark water beneath the ice of a frozen lake. Every tree holding its vascular system above, freezing through a long night. All of them little fires. All of them temporary heat sources, installed briefly on a cooling world, shining for a while, then going out. The forest in winter is full of them. The ocean is full of them. Your house, right now, is full of them. Each of them radiates heat into the cold of the night, at rates determined by their size and metabolism and insulation. All of them, in aggregate, barely dent the temperature of the atmosphere. All of them, in the long cosmic reckoning, are irrelevant to the trend. But all of them, nonetheless, are real. All of them, for as long as they last, are genuine. Imagine the sound of your own breathing, not the intellectual fact of it, but the actual present auditory experience. The slight rush on the inhale, the quieter release on the exhale, the small pauses between. Listen to it for a few cycles. That sound is the sound of a small chemical furnace at work. Each breath brings in oxygen that will be combined with carbon in the mitochondria of your cells, producing carbon dioxide, water, and a precisely calibrated amount of heat. Each breath is a small contribution to the fire that is keeping you at 310 Kelvin, in an environment that is trying, constantly, quietly, to pull you down to 2.7. This is what life is at the thermodynamic level. It is the maintenance of a temperature differential. It is the perpetual act of running a fire against a cold. The molecules of your body are, in some sense, simply a highly organized way of burning slowly enough to last a lifetime. And when a life ends, the fire goes out, the furnace stops. The body, no longer actively heated, begins to cool. Within hours, it has fallen to the temperature of the room around it. Within days, if left in the cold, it has reached whatever equilibrium the environment offers. It has rejoined the cold. The small rebellion is over, and the universe resumes its slow descent in that location, unopposed. There is something worth sitting with here, not morbidly, but honestly. The warmth of your body, which feels so essential to you, which is the carrier of every thought you have ever had, and every sensation you have ever experienced, is not owned by you. It is borrowed. It is a small amount of energy extracted from food, organized by cellular machinery, broadcast briefly as your particular temperature, and then released back into the universe. The universe lent you that heat. The universe will collect it back, eventually. The cold is patient. The cold is always, in the last analysis, going to win. But the cold does not win spitefully. It is not malicious. It is not even aware of the warmth it is gradually absorbing. It is simply what the universe tends toward, the way water tends toward its level, the way a balanced system tends toward equilibrium. The cold is not an enemy. It is the shape of the container. Picture yourself now at the center of a small circle of warmth. Your body, your breath, the small microclimate of heat that surrounds you, extending perhaps a few centimeters into the air before dissipating. Just beyond that circle, the room. Beyond the room, the walls. Beyond the walls, the neighborhood at whatever temperature your climate currently provides. Beyond the neighborhood, the continent. Beyond the continent, the planet, radiating its patient warmth into the surrounding cold of orbit. Beyond the planet, the thin, warm atmosphere and the thin, warm oceans and the thin, warm crust. Beyond all of that, nothing. Nothing, and the cold. You are a small warmth inside a slightly larger warmth inside a larger warmth still, nested inside a cosmos that is almost entirely not warm. If you were to zoom out from yourself on a scale of temperatures rather than distances, to map not where the matter is, but where the heat is, you would see a thin shell of warmth at your body's surface, a larger shell of tolerable warmth at the atmosphere's surface, a thin interplanetary glow that is already effectively cold, and then an almost uniform 2.7 Kelvin field extending in every direction, forever, unbroken except for the occasional warm pinpoint of another star, another world, another small rebellion somewhere in the dark. This is the map you have been carrying unknowingly all your life, a map of where warmth exists, and warmth on this map is vanishingly rare. There is a word for what you are doing from the cold's point of view. You are a temporary disequilibrium, an unequalized patch, a small knot of not yet cold, sitting in a fabric that is otherwise very close to fully cooled. Your life is the process by which that knot slowly unravels. It will unravel quickly if your circulation fails, more slowly if your metabolism falters, and on a longer timescale inevitable to all things, as your cells exhaust their ability to repair themselves, and your body gradually loses its capacity to sustain the fire. At every pace, the direction is the same, toward the cold, toward equilibrium, toward the quiet temperature of the photons that have been passing through you, unremarked since you were born. This is not a tragedy, or rather, it is a tragedy only if you insist on measuring it against some alternative scenario in which the warmth persists forever, which is not an available option, which is not consistent with the laws of the universe, which has never been the case for any living thing that has ever existed on any planet we have been able to examine. The warmth is temporary, because warmth is what temporary looks like. Permanence, in the universe we actually live in, is cold. And perhaps there is something to be said for loving the warmth all the more, precisely because it is borrowed. The cup of tea you drink while the rain falls outside, the specific weight of a blanket on a cold night, the way a sunlit patch of floor attracts every animal in the house, and also, if you are honest, attracts you. These are not just sensory pleasures. They are small, specific rebellions. They are moments when you, a temporary warmth in a cooling world, notice and cherish another, smaller temporary warmth, because both of you are participating in the same quiet act of defiance against a backdrop that is, on the whole, indifferent to you. There is an old image from the philosophers of ancient Greece of a fire at the center of a great dark hall. People gather around it. They speak. They tell stories. They eat. They pass in and out of its circle of light. The fire, in this image, is life. The hall is the world. The dark that surrounds the hall is what the fire holds back. We know now, in a way the ancient Greeks could not have known, that the image is more literal than they intended. The fire really does hold back something. The fire really does push against a cold that is real and measurable and extensive beyond imagining. And the fire really is small and really is temporary and really will, in its time, go out. But while it burns, it is beautiful. While it burns, it is the whole reason there is anyone in the hall to notice. While it burns, the cold is kept at bay by the simple, astonishing fact that here, for now, matter has organized itself into a pattern that resists equilibrium. You are that pattern. Your body, tonight, at whatever temperature it currently holds, is one of the small points on the map where the cold is being actively, locally defied. And you are going to continue defying it, breath by breath, heartbeat by heartbeat, for however long you are lucky enough to do so. That is enough for the moment. That is enough to hold. Now let us come back from the hilltop. Let us bring with us everything we have learned. Let us descend one last time into the final cold. Not the cold of any particular place, but the cold as an idea, the cold as direction, the cold as the answer to a question. Human beings have been asking in various forms for as long as they have been looking up at the sky. Consider, for a moment, the people who first understood what we are now discussing. Not the physicists who measured the temperatures, the earlier ones. The Polynesian navigators who set out across the Pacific in double-hulled canoes 1,000 years ago, reading the stars at night to find islands whose existence they could only infer from patterns of current and bird flight. Those navigators stood on the decks of their canoes on nights when the air was clear and the wind was cold, and they looked up. They did not know the temperature of the stars. They did not know what the stars were made of. They did not know the distances involved. But they knew, in a way that is perhaps older than knowledge itself, that the stars were fire. That the sky around the stars was not fire. That the darkness between was something else, something other, something that went on past the horizon and beyond. That intuition was correct. They were looking across thousands of years of history they could not have foreseen at the same cosmic microwave background that Penzias and Wilson would later hear as static in a New Jersey antenna. They were looking at the cold. They were registering with their bodies and their senses and their carefully cultivated attentiveness to the sky, the existence of a vast, dark, not warm region that surrounded them on all sides, and against which the small warmth of their island, their canoe, their fire, and their own bodies was the only defense they had. They navigated. They crossed thousands of kilometers of open ocean in small boats under those stars, in that cold. They reached Hawaii, reached Rapa Nui, reached Aotearoa, reached islands so far apart that for centuries Europeans could not believe they had been settled by the same people. The Polynesian navigators accomplished something that, from the perspective of any civilization without their specific body of knowledge, looks impossible. And they accomplished it by paying close, patient, warm-bodied attention to a cold, dark sky. There is a lineage here that is worth naming: the Polynesian navigators, the Chinese and Arab astronomers who mapped the stars over centuries, the European natural philosophers who, one by one, began to ask quantitative questions. How hot is a flame? How cold is ice? What is the lowest temperature that can be achieved? Guillaume Amontons in France in 1702, who first suggested that there might be an absolute lower limit to temperature. Lord Kelvin in Glasgow in 1848, who formalized the concept of absolute zero and gave us the scale that still bears his name. Onnes in Leiden in 1908, liquefying helium for the first time. Penzias and Wilson in Holmdel in 1964, hearing the echo of the beginning. Cornell and Wieman in Boulder in 1995, creating a Bose-Einstein condensate. The ALMA team in Chile in 2013, measuring the Boomerang Nebula's impossibly low temperature. Every one of them, a link in the chain. Every one of them, a warm body asking a cold question. And all of them, in their own ways, doing what the Polynesians did, navigating by the cold, using the existence of the dark and its temperature and its geometry and its extent to figure out where they were and where they were going. Here is what is worth noticing. Every civilization, every culture, every thoughtful human being who has ever seriously contemplated the night sky has arrived at a similar conclusion about the structure of things. The warmth is small. The cold is large. The warmth is brief. The cold persists. The fire in the hearth is precious precisely because the dark is so vast. This is not a pessimistic view. It is not, in fact, a view about tragedy at all. It is, more accurately, a view about context. It is the understanding that warmth does not come for free, that the conditions permitting life are specific and local and temporary, and that the universe we actually inhabit is not the one our sensory systems have been tuned to assume. Our bodies feel as though warmth is the default and cold is the intrusion, because that is how it is on the small sliver of the Earth's surface where we live. But that is not how it is. That is the reverse of how it is. Once you have grasped this, a strange thing happens. The universe does not become colder to you. It becomes warmer, because every fire you now notice, every star, every campfire, every cat, every lit window, has the full weight of cosmic context behind it. You see now what each one is working against. You see now how much cold each small warmth is holding back. You see now that the universe is not defined by the cold that fills most of it, but by the warm deviations from that cold that manage, against the odds, to persist for some time in some places. The universe is defined, in other words, by exceptions, and you are one of them. Every campfire you have ever sat beside was holding back, with its small orange circle of warmth, a cold that extends unbroken from your skin to the cosmic microwave background. Every light left on in a window across a dark field was a rebellion of the same shape. Every star visible in the sky above that field was doing the same thing on a vastly larger scale. A fusion furnace burning hydrogen into helium, pouring out heat into a cold that swallows most of that heat without ever warming noticeably. And every galaxy is a collection of such stars, and every cluster of galaxies is a collection of such galaxies. And the whole of the visible universe is, in this way of looking at it, a scatter of small fires in a vast, cold hall. The fires will go out, one by one over scales of time that dwarf every human measurement. The sun will go out in about 5 billion years, swelling into a red giant before collapsing to a white dwarf that will itself cool, slowly, patiently, over tens of billions of years, until it becomes a cold, inert stone drifting in a cold, inert galaxy. The other stars will follow. New stars will be born from the remaining gas for a while, but the supply of gas is finite, and eventually the last star will form, and then burn, and then go out. And then the galaxies will go dark, and then the black holes that remain will evaporate, over timescales so long that the numbers stop conveying meaning. And then even the black holes will be gone, and the universe will be, at last, what it has always been tending toward being. Quiet, dark, cold. This is the last page of the story, but the last page is not the whole story. We began tonight by looking at your breath on a winter morning, that pale cloud in the cold air, a small visible sign of the warmth inside you, meeting the slightly less warmth outside you. And we said at the very beginning that to the universe, that cloud of breath is almost indistinguishable from boiling water. That minus 10 degrees Celsius is, on the cosmic scale, a warm afternoon. Now you understand why. We have descended, layer by layer, through the cold of this universe. We started at your body, at 310 Kelvin. We stepped outside into winter at 260. We stood on the East Antarctic plateau at 175, where breath freezes into the whisper of the stars. We climbed 300 kilometers into low Earth orbit, to the shadow of our own planet, where the temperature on the dark side of a solar panel falls to 120 Kelvin every 45 minutes. We traveled to the south pole of the moon, into craters like Shackleton and Shoemaker that have not seen sunlight for billions of years, and we found temperatures of 25 Kelvin waiting at the bottom, patient, preserving ancient ice from before the oceans of Earth were full. We pushed outward through the solar system, past Jupiter, past Saturn, past Neptune, out into the Kuiper Belt and the Oort cloud, where distant cometary surfaces sit at 10 Kelvin and water ice behaves like bedrock. We crossed the boundary of the solar system and arrived at the baseline of the universe itself. 2.7 Kelvin, the cosmic microwave background, the faint, lingering warmth of the Big Bang cooled by 13.8 billion years of expansion. We visited the Boomerang Nebula, 5,000 light-years away, where a dying star's exhaled gas has cooled to 1 Kelvin, a pocket of matter colder than the universe that contains it. And we went inside our own laboratories, into chambers in Boulder and Cambridge and Bremen, where human ingenuity has produced temperatures measured in billionths and trillionths of a Kelvin, temperatures with no natural counterpart anywhere in the observable cosmos. 7 layers, 7 steps down from the warmth of your skin to the floor of matter itself. And then, beyond those layers, we followed the arrow further into the deep future. We watched the cosmic microwave background continue to cool, stretched by the ongoing expansion of the universe, toward temperatures so low they approach absolute zero. We saw that the universe's tendency, its direction, its underlying grain, is toward cold. That warmth is the anomaly. That the fires in the sky and the fires in our bodies and the fires in every cell of every living thing are all, in the long cosmic accounting, temporary deviations from a background that is, on average, almost entirely dark. We asked why. Why does the universe slide toward cold? Why does entropy increase? Why did the Big Bang produce a low entropy state that has been unspooling ever since into the cooling distribution we now inhabit? And we admitted, honestly, that we do not know. That some of the best minds working in physics today, Roger Penrose, Sean Carroll, others, have spent their careers trying to answer this question and have produced only speculation. That the arrow of cold is the deepest empirical fact we have and the least explained. We asked what cold really is at the quantum level, and we found that even there, at the absolute floor, motion does not fully cease. That the uncertainty principle forbids perfect stillness. That absolute zero is not a place any matter can actually occupy, but a limit it can only approach. That the floor of temperature is not a wall you can rest against. It is an asymptote. It is a direction, not a destination. And then we came back. We came back from the deep future, from the heat death, from the quantum floor, and we stood again on a hilltop on a winter night, looking up at stars that suddenly looked different, harder, sharper, more improbable. Each one a fire holding back a cold we now understood the extent of, each one a rebellion. We remembered the Polynesian navigators who crossed the Pacific by reading the cold sky. We remembered the chain of scientists from Amundsen's, through Kelvin, through Onnes, through Penzias and Wilson, through the modern laboratories that have pushed the coldest measurements ever taken. We saw that every human being who has seriously contemplated the night sky has arrived in one form or another at the same conclusion. The warmth is small, the cold is large, the fire is precious because the dark is so vast, and that is, in the end, the shape of what we have found. Not that the universe is cruel, not that the universe is indifferent, not that your warmth is meaningless because the cold will eventually reclaim it, but that your warmth is precisely and exactly meaningful because of the cold, that the rarity of the fire is what makes the fire worth tending, that every small, temporary, improbable hotspot in the cosmos, every star, every planet capable of supporting life, every living body, every thought inside every living body is an exception, and exceptions in a universe that tends overwhelmingly toward cold are the only thing worth noticing. Your breath on a winter morning, the breath we began with, is such an exception. It is a small cloud of warm, moist air, briefly organized by the chemistry of your lungs, released into a cold that is patient and vast and everywhere. It condenses. It hangs for a moment in the frigid air. It dissipates. It is gone. But while it was there, it was real. While it was there, it was warmer than almost all the matter in the universe. While it was there, it was a small, specific act of defiance, one among uncountable others being performed at that same moment by other living things on other parts of the planet, and, for all we know, perhaps on other planets around other stars. Look at your breath on a winter morning now, knowing what it is, knowing what surrounds it, knowing what it is pushing back against, knowing that the pale cloud you release is, briefly, a warm thing in a cold place, and that the cold place is not the exception, but the rule. The cold does not hate you. The cold does not want you. The cold is simply what the universe is, once you strip away the small warm places where everything interesting, including you, happens. And you, tonight, are one of the small warm places. You are holding 310 Kelvin against 2.7. You are burning food slowly in the mitochondria of your cells. You are radiating a small, steady glow of infrared into the air around you, a glow that, if you had the right camera, you could see as a soft outline of warmth in the shape of your body, shining gently into the dark. You are, at this moment, doing exactly what every star does, holding back for a while the one thing the universe is trying to do. If this changed how you think about cold, if the winter air from now on feels a little less like an enemy and a little more like the quiet shape of the universe you live in, then the time was well spent. If you find yourself, tomorrow or next week or next year, on a cold, clear night, looking up at the stars and feeling for a moment the full weight of what sits between you and them, and also feeling, simultaneously, the warmth of your own breath in the air in front of your face, and recognizing both of these as part of the same deep story, then what we have done here together has mattered. The cold is going to be there, always, everywhere you cannot see, and in most of the places you can. It was here before you arrived. It will be here when you are gone. It is the slow, patient, permanent background of the universe, and it has been cooling for 13.8 billion years, and it will continue cooling for longer than any human imagination can hold. But tonight, right now, while you are listening to this, you are warm. Your body is holding its temperature. Your breath is moving in and out. Your heart is delivering warm blood to every part of you, and the small circle of warmth around your body is extending a few centimeters into the air and then dissipating, like the breath of someone on a winter morning, into a cold that is, at this moment, a little less cold than it would have been without you. That is what you are, not a permanent thing, not a cosmic inevitability, not a fixed point in the structure of the universe. You are a small, temporary, improbable warmth in a cold that is otherwise almost unbroken. And you have, for as long as you have, the simple, astonishing ability to notice that fact, to feel your own warmth, to see your own breath, to look up at the stars on a winter night, and know now what you are looking at and what is looking back. Thank you for staying through this exploration with me. Thank you for the time and for the attention and for letting the weight of a cold universe settle tonight into something that feels not like fear, but like context. Thank you for being, for the length of this video, one of the warm things noticing the cold. Sleep well. The cold will still be there in the morning. So will you.